We know in a chemical reaction, there is a reactant side and a product side. Many chemical reactions are reversible, meaning the chemical reaction proceeds in both directions, and this is indicated by the double arrow. Your reactant forming a product is called the forward reaction, and the product reversing and forming the reactant is called your reverse reaction. In a chemical equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. Also, the ratio of products and reactants is constant, meaning the amount of reactant and product does not change, it stays the same. Chemical equilibrium is kind of like a seesaw effect, where you have reactants on one side and products on another. If the reactants dip too low, the system will make a change as to keep the reactants and products even again. And if the products dip too low or go too high, then the system is again going to try and make the reactant and product balance again. Lastly, the forward and reverse reaction never stop moving. They continuously move in order to keep the balance of equilibrium. So a system that is at equilibrium never goes into completion. It keeps working and keeps moving. You can see in the visual here, the forward reaction is moving towards the product. At this very same time, the reverse reaction is moving towards the reactants. Le Chatelier's principle states that if an external stress is applied to a system at equilibrium, the system will adjust to reestablish in order to maintain equilibrium. By the way, system refers to the reactant and product as a whole. Factors or stressors, as we call them, that affect equilibrium are heat, pressure and volume, and concentration. If we add stress to a system, there will be some type of system adjustment made in order to bring it back to equilibrium. For example, if generally we increase the heat, the system will lower the heat. If we increase the pressure by decreasing the volume, the system will try to decrease the pressure by increasing the volume. And if we increase the concentration of one side of the system, it will try to decrease the concentration. Basically, according to Le Chatelier's principle, whatever stress is done to the system, it will try to undo it. This creates a nicely balanced system. And what are we balancing exactly? We're balancing the concentration of product on one side and reactants on another. Now that we have a general idea of Le Chatelier's principle, let's look at a generic chemical equation and apply Le Chatelier's principle to it. It is always important to make note of what state the substances are in. Here we have A as a solid, B as a gas, a double arrow indicating the system is in equilibrium, C as a gas, and D as a liquid. This chemical equation is in equilibrium, meaning the system is dynamically moving in both directions at one time. So the forward reaction and reverse reaction are both moving in two directions at one time. The forward reaction rate equals the reverse reaction rate, and the concentration of reactants and products remains constant. A system will shift to the right or left in order to maintain equilibrium. If there is a shift to the left, this will increase the reactants and decrease the products. If there is a shift to the right, this will increase the products and decrease the reactants. Again, stressors that change the equilibrium are concentration, heat, and pressure and volume. Let's look at how concentration affects the chemical equilibrium first. If we increase the concentration of B, will the system shift to the left or to the right? It will shift to the right. It does this because there's an increase of reactants. Then the system needs to produce more product in order to balance out. And shift in the direction of the product will create more product. So there will be an increase in product and decrease in reactants. What if we decrease B? Will the system shift to the left or to the right? The system will shift to the left. Because there was less B reactant, the system shifted in the direction of the reactant to make more. A shift to the left increases the reactant and decreases the product. What if we increase C? Will the system shift to the left or to the right? The system will shift to the left. This will increase the reactant and decrease the product. And now what if we decrease the concentration of C? Will it shift to the left or the right? The system will shift to the right. This increases the product and decreases the reactant. Remember, Le Chatelier's principle is all about balancing both sides of the chemical equation. And that's all we're doing here. Also, remember whatever side needs to be increased will be the side the arrow will point towards. And that is where the shift will go. It will shift to the right if product needs to be increased, or it will shift to the left if reactant needs to be increased. What about if we increase and decrease the concentration of A? Well, A is a solid, and solids have no effect on the equilibrium shifting, so the concentration of A going up or down will have no effect. Now, the same goes for D. D is a liquid, and liquids also have no effect on the equilibrium. So if we increase or decrease the concentration of D, it will have no effect on the equilibrium. Basically, only gases will have an effect on the equilibrium. We know now how concentration has an effect on equilibrium. Let's see how heat affects equilibrium. Before evaluating the equilibrium shifts, we must first understand the difference between endothermic and exothermic reactions. In an endothermic reaction, energy is used or absorbed by the reactant in order to make the product. Because the reactants are using heat, you sometimes will see the heat written with the reactants or on the reactant side. On the contrary, in exothermic reactions, energy is given off or released by the reactants to create the product. So you may see heat written on the product side because heat is being released on this side. If heat is added to an exothermic reaction, the system will shift to the left. And if heat is added to an endothermic reaction, the system will shift to the right. It is important that you are able to identify an exothermic and endothermic reaction before determining which way the system will shift. Let's look at an example using this generic chemical equation. So here we have heat written on the reactant side, and that tells us that this is a endothermic reaction, right? If we increase the heat of this endothermic reaction, will the system shift to the right or the left? It will shift to the right. And if we decrease the heat of this endothermic reaction, will it shift to the left or the right? It will shift to the left. Okay, let's compare this endothermic reaction to an exothermic reaction. We have heat on the product side, which means this is exothermic. It's a hint that it's exothermic, right? If we increase the heat here, will the system shift to the right or to the left? It will shift to the left. And if we decrease the heat, which way will the system shift? It will shift to the right. If this is still confusing you, take some time to stop the video and look at the patterns here. Again, remember this rule. If heat is added to exothermic, there will be a shift to the left. And of course, if heat is decreased on an exothermic, the system will shift the opposite direction, so to the right. And for endothermic reactions, it's also opposite. If heat is added, the system will shift to the right. And if we do the opposite, meaning we decrease the heat, the system will move to the left. Okay, next let's look at how pressure and volume change the equilibrium. First off, let's make sure we understand how pressure and volume are correlated. This illustration shows atoms in a cup and a plunger on them controlling the volume and pressure. Pulling up on the plunger increases the volume and decreases the pressure. In contrast, pushing the plunger downwards decreases the volume and increases the pressure. So remember, increased volume equals decreased pressure, and decreased volume is equal to increased pressure. Changes in pressure are only significant if gases are present in the system. If pressure is increased, the system will shift to the side with the least moles of gas. And if pressure is decreased, the system will shift to the side with a greater amount of moles of gas. So let's look at an example. If we increase the pressure here, will the system shift to the right or to the left? An increase in pressure will shift the system to the side with less gas. So first let's count the moles of gas on both sides. On the reactant side, we have 1 mole of gas, and on the product side, we have 2 moles of gas. Since we have less gas on the reactant side, the system will shift towards the reactants. It will shift to the left. Now, what if we decrease the pressure? Will the system shift to the right or to the left? If we decrease the pressure in a system, the system will shift in the direction of more moles of gas. So our system will shift to the right. Okay, let's sum up what we have learned. When we say a system is at equilibrium, it means the system is dynamically moving in both directions at one time. The forward reaction rate is equal to the reverse reaction rate, and the concentration of reactants and products remains constant. The stressors that perturb equilibrium, in other words, they have the ability to change equilibrium, are the concentration of the reactant and product, heat, and pressure/volume. Also, remember Le Chatelier's principle and how it relates to equilibrium. The principle states that if an external stress is applied to a system at equilibrium, the system will reestablish in order to maintain that equilibrium. Alrighty, moving on to our next topic, reaction rates. Reaction rate is the change in concentration of reactants and products over time. For a chemical reaction to take place, molecules must collide with each other with enough force, greater than the activation energy, and they must collide at the correct place on the molecule. This area is called the reactive site. Let's break this sentence up a bit more. The activation energy is referring to the minimum amount of energy needed to start a chemical reaction. When two molecules collide, they must have enough energy to overcome the minimum activation energy. And the lower the activation energy, the faster a reaction can act. The higher the activation energy, the slower a reaction will act. The reactive site is referring to the specific area where the molecule needs to collide, or else it won't be able to break or bond. These two terms are often confused with each other, so remember, activation energy has to do with energy needed for the molecules, and the reactive site has to do with the site, obviously, an area on the molecule that is pretty much like a sweet spot for a chemical reaction to take place. Factors that affect the reaction rate are temperature, concentration, surface area, and catalyst. Increasing temperature will increase the reaction rate. Increased temperature makes molecules move faster. This increases the kinetic energy they have when colliding with each other, thus increasing the chance that sufficient energy will be transferred during the collision. Increasing temperature also increases the number of collisions because the molecules are moving faster. Increasing the concentration of the reactants or pressure if gases are involved increases the reaction rate. This is due to the fact that there are more molecules to collide with and react with. Increasing surface area of a solid, normally done by crushing a substance or cutting it into multiple pieces, allows for more space on the substance to interact with collisions. Lastly, adding a catalyst to the reactant will speed up the reaction rate. It does this by lowering the activation energy needed to create a chemical reaction. Let's emphasize a bit more on the catalyst. Adding a catalyst to the reactions will speed up the reaction rate. It does this by lowering the activation energy needed to create a chemical reaction. Let's look at a visual of this concept. We have time increasing as we go left to right on the x-axis, and energy increasing as we go up the y-axis. The blue line represents a system, a chemical equation. On the left, we have the reactants, and on the right, we end with the products. At the peak of the line is the transition state. The area from the beginning of the reactants to the transition state is the activation energy. The blue line represents our uncatalyzed reaction, meaning there is no catalyst present. And our pink line will represent our catalyzed reaction, meaning there is a catalyst present. Notice the pink catalyzed reaction has a lower activation energy, meaning it will take the reactant less time to reach the transitional state and become products. That is how a catalyst speeds up a chemical reaction. It does so by lowering the activation energy. Other important things to remember about catalysts are that they can be used without being consumed, meaning they are reusable. Also, biological catalysts are called enzymes. So let's do a quick comparison of both topics we just went over, equilibrium and reaction rate. Equilibrium relates to balance in the system, how the concentrations of products and reactants in the system are balanced, and the rates forward and reverse reaction are also balanced. Reaction rate relates to speed, the rate at which the forward and reverse reaction are in. The connection between the two is that at equilibrium, the reaction rates are equal to each other. Before we go over some practice problems, I just want to show you this chart I developed. It's not super thorough, but it's sort of a shortcut reference if you're still getting the hang of it. You can screenshot it and use it on the side to look at while you're doing your practice problems. Also, just a warning, do not try and memorize the chart and bypass understanding the whole concepts because you will get very lost. This is just a supplemental chart. Also, keep in mind, I didn't write the opposites of each other. So, for example, I'm assuming you should understand that if we decrease the temperature for endothermic, it will shift to the left. And for exothermic, it will shift to the right, and so on. Okay, so let's get into these practice problems. All of these are straight from the official ATI T7 study manual. I thought I'd go over them so you can get used to the wording because honestly, the wording ATI uses is honestly a little funny and different. So, starting with question number 1. Equilibrium would favor the reactant side if which of the following occur? By the way, when you see the word favor, it means shift towards, okay? So shift towards. So this means equilibrium would shift towards the reactant side if which of the following occurred. So A, if H2O is added. H2O is a product here. If we add product, the system will shift towards the reactant in order to balance it out. Or we can say the system will favor the reactant side. Same thing. So this is our answer here. This is our correct answer. B, if we decrease the temperature, well, we know this is an exothermic reaction, right? Because we see the heat on the product side. So remember our rules for exothermic reactions. If we increase the heat, it will shift to the left. If we decrease the heat, it will shift to the right. So here, temperature is decreased on an exothermic reaction. So the shift will be towards the products. So that makes this B wrong. Next, if carbon monoxide is added. Well, carbon monoxide is a reactant. So increasing our reactant will cause the system to shift to the product side. And if we remove methane, methane is from the product side. The system will shift towards the product side in order to compromise. So all of these are wrong and our answer A, H2O, is right. Awesome. So next question. A substance that lowers the activation energy is which of the following? Our answer here is catalyst. So this question comes up a lot on the practice questions. Make sure you know exactly what a catalyst does and what it's used for and how it relates to reaction rates. Alrighty, next question. Which of the following would increase the forward rate of the gas phase reaction? Okay, so first, I just want to point out that the forward rate is going this way, from the reactant to the products. So the question is only referring to increasing the rate in that direction from left to right. A, if we add a carbon monoxide to the reactant side, this will definitely increase the rate of the reaction because increasing the concentration of reactant will increase the forward reaction rate. B, increasing the temperature. First off, we have an exothermic reaction. If we increase the heat on an exothermic reaction, the forward rate slows down and the reverse rate speeds up. So this does not increase the forward rate, it slows it down. How about adding H2O? H2O is adding more product, so the system will shift towards the reactants. This increases the speed going towards the reactants, but it decreases the speed going towards the products, that being the forward rate. So here the forward rate slows down. Lastly, increasing the pressure. Increasing pressure equals increasing heat. As you increase the pressure, you're also going to increase the heat in a system. So this is exactly what happens in answer B scenario. The increase in heat on an exothermic reaction will decrease the rate of the forward reaction. By definition, a mole is a measurement of how many particles, atoms, or molecules are in a substance. The abbreviation for mole is mole with a lowercase m. 1 mole is equivalent to exactly 6.022 times 10 to the 23rd particles. This number is, of course, in scientific notation. If we expand it out, the number would be gigantic. It actually would equal 602 hexillion. But because working with such a large number with so many zeros would be impossible, we condense it and say 6.022 times 10 to the 23rd, and it makes it much more manageable to work with. By the way, this number is referred to as Avogadro's number. It's pretty important to remember that Avogadro is a very important guy. He made a significant contribution to the theory associated with the mole. So remember, this number represents Avogadro's number. Okay, so we know 1 mole tells us a quantity and represents a number. Think of it like this. 1 dozen eggs is much like 1 mole of eggs. 1 dozen represents the number 12, and 1 mole represents the number 6.022 times 10 to the 23rd. So we can say we have 1 dozen eggs, and we can also say we have 1 mole of eggs. Remember, a mole tells us the quantity and represents a number. We have 1 mole of carbon, and that would be equal to 6.022 times 10 to the 23rd atoms. We can also have 1 mole of a compound like CO2, and this would be equal to 6.022 times 10 to the 23rd molecules. In fact, we can have 1 mole of anything, and it will be equal to 6.022 times 10 to the 23rd particles. Notice how I use the words atom to describe 1 mole of carbon, molecules to describe 1 mole of CO2, and the word particles to describe 1 mole of anything. You can use any of these words to describe a mole of something because it's in the definition, but you must use the terms correctly. Particles is referring to both molecules and atoms. Particles is kind of like an umbrella, and molecules and atoms are underneath it. The definition of the word particle is a basic unit of matter and energy, such as molecules, atoms, protons, neutrons, electrons, or photons. The difference is atoms is used to describe one type of substance like an element where all the atoms are the same, such as carbon. So carbon is only made of carbon atoms, so we refer to its particles as atoms. And molecules describes a compound like CO2. Carbon dioxide is made of 2 different types of atoms bonded together. If we have 1 mole of carbon dioxide, we have a mole of these molecules. So we refer to the particles in the compound as molecules. And 1 mole of anything, we can describe this as particles because particles is the general term. Remember, particles is like the umbrella term, and atoms and molecules are beneath it. Let's try some practice problems. How many atoms does 1 mole of gold have? Yes, 6.022 times 10 to the 23rd atoms. And how many molecules does 1 mole of water have? Awesome, 6.022 times 10 to the 23rd molecules, correct. Okay, so now that we have a general understanding of what a mole is, what is molar mass? Molar mass is the weight of 1 mole in a substance measured in grams per mole. That means grams and moles are proportional to each other. As one increases or decreases, the other does the same. Let's say we have 3 piles of atoms. Each pile of atom is exactly 1 mole. Therefore, we can say each pile of atoms is Avogadro's number, or 6.022 times 10 to the 23rd atoms. Now, let's say the first pile is all carbon atoms, and the second pile is all nitrogen atoms, and the third pile is all sulfur atoms. How much will each 1 mole of atoms weigh? Will there be a difference in the weight of each pile of atoms? So this number we know represents the atomic mass, but it also represents the molar mass. So 1 mole of carbon atoms weighs 12.009 grams. In short, we can write it like this, 12.009 grams per 1 mole. Nitrogen has a molar mass of 14.006, so 1 mole of nitrogen atoms weighs 14.006 grams. And we can write that out like this. Sulfur has a molar mass of 32.059, so 1 mole of sulfur atoms weighs 32.059 grams. Each of these that we just calculated are the molar mass. So each different element or substance is going to have a different molar mass. Okay, so just to reiterate this concept once more, let's look at sulfur right off of the periodic table. This number represents the atomic mass in AMU, atomic mass units. But it also represents the molar mass in grams per mole. Remember, this molar mass refers to how much 1 mole of sulfur weighs in grams. Our number is 32.059, so that means 1 mole of sulfur weighs 32.059 grams. Okay, so let's put all of that information together and see what we get. 1 mole of sulfur is 32.059 grams. 1 mole of sulfur is also equal to 6.022 times 10 to the 23rd atoms. Therefore, 32.059 grams of sulfur is equal to 6.022 times 10 to the 23rd atoms. So we can see there's a relationship between not only moles to grams, moles to number of atoms, but also grams to number of atoms. Okay, so let's use this information we learned to answer the next couple of questions. How many grams does 1 mole of carbon weigh? Use the illustration given. $12.009 grams, right? 1 mole of carbon weighs 12.009 grams because remember, that little number is grams per mole. So 12.009 grams per 1 mole. And how many grams are in 4 moles of carbon? We simply need to multiply 4 moles by the number of grams of each mole, and we get 48.036 grams. How many grams does 1 mole of zinc weigh? And just FYI, on the TEAS exam, if you're presented with a mole question, they will provide all the necessary information to make a calculation. No way do they expect you to remember the atomic mass or molar mass of elements. Right, 65.38 grams. 1 mole of zinc weighs 65.38 grams. And how many grams are in 9 moles of zinc? If we multiply the number of moles given by the mass of each mole, we get 588.42 grams. Awesome. So we've gone over how to find the molar mass. Now let's go over how to find the molecular mass. First off, what is molecular mass? Molecular mass is the sum of the atomic masses, the AMU, and the entire molecule. And just as a side note, remember atomic mass is equal to the molar mass. So how do we find the molecular mass? The best way to understand this is jumping right into some practice problems. So let's get to it. What is the molecular mass of glucose? The first step is finding these on the periodic table so we can get their molar masses. Now, we're going to break this compound down by each element one by one. Looking at carbon first, the little 6 subscript tells us that we have 6 carbon atoms here. So we're going to write down 6, and the molar mass is 12.009. So we're going to multiply 6 times 12.009, and we get 72.054. Next, we have hydrogen. The little 12 subscript tells us that there are 12 hydrogen atoms in glucose, and the molar mass tells us how much each of those atoms weigh. So we multiply 12 times 1.0078, and we get 12.0936. Oxygen has 6 atoms in glucose, and each weighs 15.999, so we multiply 6 times 15.999, and we get 95.994. We now have the individual masses of each different type of atom in glucose. Next, we just have to add them up to get the entire molecular mass. If we plug that into our calculators, we get 180.1416. However, when adding numbers, the rule of sig figs is to round to the least number of decimal places. To do this, we look at the number of decimal places in the numbers we add up and look for the least amount. So 0.054, 0.0936, and 0.994 seems like 3 digits is the least after the decimal point. So our answer will only have 3 digits after the decimal point. And that's the correct number of sig figs. So we're going to round up to 180.142 grams per mole, and that's our answer. Let's find the molecular mass of calcium nitrate. First, we get our elements off the periodic table, and then we identify the masses one element at a time. Calcium has no subscript, so there is only 1 calcium in the compound. So we're going to write 1 times the molar mass, 40.078, and this gives you 40.078. There are 2 nitrogen, indicated by the number 2 subscript, so we're going to multiply 2 times 14.006, and this gives us 28.012. Lastly, oxygen has 6, so we're going to multiply 6 times 15.999, and we're going to get 95.994. We add these all together and get a total molecular mass of 165.084 on our calculators. This is the correct number of sig figs, so we're going to leave the number at that. And of course, we have to put our units, grams per mole, and that's our answer. Let's try one more. Let's find the molecular mass of ammonium phosphate. We have our elements off the periodic table for reference here. Starting off with nitrogen, we have 3 nitrogen in our molecule, multiplied by the molar mass, 14.006. That gives us 42.018. Next, there are 12 hydrogen atoms here, multiplied by the molar mass, 1.0078, and we get 12.0936. Phosphorus, we just have one atom, so 1 times 30.974, that's going to give us 30.974. Lastly, oxygen. There are 4 oxygen atoms in ammonium phosphate, so we multiply that by the molar mass of 15.999 and we get 63.996. Now, we add all of these masses all up together to get our molecular mass, and on our calculator, we get 149.0816. Our least number of digits after the decimal are 3. And by the way, if you're not sure what I'm referring to, it's these. 0.018 has 3 digits, 0.0936 has 4 digits, 0.974 has 3 digits, and 0.996 has 3 digits. So the least amount of digits after our decimal point in the numbers that we're adding up is 3. So our answer needs to have 3 digits after the decimal place. So our final answer is 149.082 grams per mole. Now, what if I were to ask you to find the molar mass of nitrogen in ammonium nitrate? Awesome, yes. 42.018 is the molar mass of nitrogen in ammonium phosphate. Okay, there is one last thing I want to share with you. It's probably something you're familiar with, and it's a very easy thing to remember. So we have a chemical formula here, and do you remember what the coefficient represents? The coefficient represents the number of atoms or molecules on a microscopic level. However, it also represents the number of moles on a macroscopic level. Now, if you're confused and wondering why that is, I know it's confusing, but I'm not going to go over it in this particular video, so I will probably make another video on that. But for now, just accept the fact that the coefficients can represent both the moles and the number of atoms and molecules. So for example, in this chemical formula, there are 4 moles of iron that react with 3 moles of oxygen, and this creates 2 moles of iron 3 oxide. This last practice problem I'm leaving you with is from the official ATI T7 practice questions. It says, balance out the chemical equation. Which of the following best describes the number of moles of each product after the equation is balanced? So if we balance this out and look at the product side, also make sure you're looking at the product side. Don't accidentally select the answer that describes the reactant side, okay? So looking at the product side, we see we have 1 mole of magnesium chloride and 2 moles of water. So the correct answer ATI gave was written out like this. So you'll either be given the density and mass, and then you have to solve for the volume, or you'll be given the density and volume and have to solve for the mass, or you'll be given the mass and volume and have to solve for the density. I like to use the pyramid method as a guide. Inside the pyramid, we have density, mass, and volume. If we want to find the density, we divide mass by volume. If we want to find the volume, we divide mass by density. And if we want to find the mass, we multiply density times the volume. The best way to understand the concept is, of course, by practicing. So let's get to it. Our first problem says we have a cake with a mass of 500 grams and a volume of 2,500 cubic centimeters. What is the density of the cake? Well, we're given the mass of 500 grams and we're given the volume of 2,500 cubic centimeters. If we look at our pyramid, it tells us to divide mass by the volume to get the density. So the density is going to be 500 grams over 2,500 centimeters cubed. If we punch that into our calculator, we get 0.2. And we don't need to convert any of the units here, so we keep it as is. So the final answer is grams over cubic centimeters. A beaver has a piece of wood with a mass of 6.0 grams and a volume of 12.0 centimeters cubed. What is the density of the wood? Well, we're given the mass of 6 grams and the volume of 12 centimeters cubed. If we look at our pyramid again, it tells us that density equals mass over volume. So we're going to do 6 grams over 12 centimeters cubed as our volume. If we punch this into our calculator, we get 0.5 grams over centimeters cubed. The density of the chocolate is 8 grams over centimeter cube. If the sample of chocolate has a volume of 25 centimeters cube, what is the mass? Here we're given the density and the volume, and all that's missing is the mass. If we look at our pyramid, it tells us to find mass, we need to multiply density times the volume. So our density is 8 grams over 1 cubic centimeter, times our volume, that's 25 cubic centimeters over 1. If we look close, notice our centimeters cubed cancel out. If we punch this into our calculator, we get 200 grams. And remember to always double check to make sure you wrote down the correct unit. Here, we're left with grams, so our answer is going to be in grams. The flowers that were picked had a total weight of 820 grams. The density of the flowers packed together is 5 grams over centimeters cubed. What is the volume of the flowers? Well, we're given the weight that is translated to a mass of 820 grams, and we're given the density of 5 grams per cubic centimeter. We just need to find the volume. So if we look at our period, to find the volume, we divide mass by density. So we get 820 grams over 5 grams per cubic centimeter. We cancel out the grams and we're left with cubic centimeter. So if we punch this into our calculators, we get 164 cubic centimeters. The book illustrated to the right has a mass of 96.4 grams. Determine the density. Okay, so here we clearly are given the mass, but we're not clearly given the volume, which is what we need to determine the density. Luckily, we can figure this out with our illustration to the right. Remember, volume equals length times width times height. And as a side note, it does not matter the order you calculate the numbers in. The answer will always come out the same. So we plug in our numbers of length, width, and height and multiply them, and we get 163 centimeters. And let's not forget to cube this because we are multiplying centimeter times centimeter times centimeter. So 163 cubic centimeters. Okay, now that we have our mass and volume, we can finally calculate our density. Now, if we punch in 96.4 divided by 165 into our calculators, we get a very large number. How do we know how many digits to put into our answer? Well, we use significant figures. The lowest number of significant figures in our problem will be the number of significant figures in our answer. So both 96.4 and 165 have 3 significant figures in their numbers, so our answer is also going to have 3 significant figures. So our answer is 0.584 because 584 are our 3 sig figs or significant figures. Also, don't forget to round the last number if needed. So for example, if it was 0.5846, then our answer would be rounded up to 0.585. You have a graduated cylinder with 150 ml of water. You add a piece of iron that weighs 25 grams into the graduated cylinder, and the water level rises to 425 milliliters. What is the density of the piece of iron? So we know that density is mass over volume, and we clearly are given the mass in grams, 25 grams, but we're not given the volume of the iron. So we need to find the volume first, then plug it in to get the mass. The volume of the iron is going to be equal to the difference in the water volume without the iron piece and with the iron piece. So we know the volume before the iron was put in was 150 ml, and the volume with iron was 425 ml. If we calculate this, we get 275 ml. So our density is 25 grams over 275 ml. If we punch this into our calculator, we get this large number and some. How many significant figures will we have in our answer? We have 2 sig figs and we have 3 sig figs. So our answer will have 2 sig figs total, those being 9 and 0. But then we have to round the 0 to 1. So our answer is 0.091 grams over milliliter.